never go over the same line twice. But they do it recursively, and they do it with an age grade system. So the little kids learn this one, and then the older kids learn this one, and then the next age grade initiation, you learn this one. And with each iteration of that algorithm, you learn the iterations of the myth. You learn the next level of knowledge. And finally, all over Africa, you see this board game. It's called Awori in Ghana, where I studied it. It's called Mancala here on the East Coast, Bao in Kenya, Sogo elsewhere. Well, you see self-organizing patterns that spontaneously occur in this board game. And the folks in Ghana knew about these self-organizing patterns and would use them strategically. So this is very conscious knowledge. Here's a wonderful fractal. Anywhere you go in the Sahel, you'll see this windscreen. And of course, fences around the world are all Cartesian, all strictly linear. But here in Africa, you've got these nonlinear scaling fences. So I tracked down one of the folks who makes these things, this guy in Mali, just outside of Bamako. And I asked him, how come you're making fractal fences? Because nobody else is. And his answer was very interesting. He said, well, if I lived in the jungle, I would only use the long rows of straw because they're very quick and they're very cheap. Doesn't take much time, doesn't take much straw. He said, but wind and dust goes through pretty easily. Now, the tight rows up at the very top, they really hold out the wind and dust. But it takes a lot of time and it takes a lot of straw because they're really, really tight. Now, he said, we know from experience that the farther up from the ground you go, the stronger the wind blows, right? It's just like a cost-benefit analysis. And I measured out the lengths of straw, put it on a log-log plot, got the scaling exponent, and it almost exactly matches the scaling exponent for the relationship between wind speed and height in the Wind Engineering Handbook. So these guys are right on target for a practical use of scaling technology. The most complex example of an algorithmic approach to fractals that I found was actually not in geometry. It was in a symbolic code. And this was Bamana sand divination. And the same divination system is found all over Africa. You can find it on the East Coast as well as the West Coast. And often the symbols are very well preserved. So each of these symbols has 4 bits. It's a 4-bit binary word. You draw these lines in the sand randomly. And then you count off, and if it's an odd number, you put down 1 stroke, and if it's an even number, you put down 2 stroke. And they did this very rapidly, and I couldn't understand where they were getting, they only did the randomness 4 times. I couldn't understand where they were getting the other 12 symbols. And they wouldn't tell me. They said, no, I can't tell you about this. I said, well, look, I'll pay you. You can be my teacher, and I'll come each day and pay you. I said, it's not a matter of money. This is a religious matter. And finally, out of desperation, I said, well, let me explain George Cantor in 1877. And I started explaining, why it was there in Africa. And they got very excited when they saw the Cantor set. And one of them said, come here, I think I can help you out here. And so he took me through the initiation ritual for a Bamana priest. And of course, I was only interested in the math, so the whole time he kept shaking his head going, I didn't learn it this way. But I had to sleep with a kola nut next to my bed, buried in sand, and give 7 coins to 7 lepers, and so on. And finally, he revealed the truth of the matter. And it turns out it's a pseudo-random number generator. They're using deterministic chaos. When you have a 4-bit symbol, you then put it together with another one sideways. So even plus odd gives you odd. Odd plus even gives you odd. Even plus even gives you even. Odd plus odd gives you even. So it's addition modulo 2, just like in the parity bit check on your computer. And then you take this symbol and you put it back in, so it's a self-generating diversity of symbols. They're truly using a kind of deterministic chaos in doing this. Now, because it's a binary code, you can actually implement this in hardware. What a fantastic teaching tool that should be in African engineering schools. And the most interesting thing I found out about it was historical. In the 12th century, Hugo of Santillana brought it from Islamic mystics into Spain. And there it entered into the alchemy community as geomancy, the divination through the earth. This is a geomantic chart drawn by for King Richard II in 1390. Leibniz, the German mathematician, talked about geomancy in his dissertation called De Combinatoria. And he said, well, instead of using 1 stroke and 2 strokes, let's use a 1 and a 0. And we can count by powers of 2, right? 1s and 0s, the binary code. George Boole took Leibniz's binary code and created Boolean algebra, and John von Neumann took Boolean algebra and created the digital computer. So all these little PDAs and laptops, every digital circuit in the world started in Africa. And I know Brian Eno says there's not enough African computers, but You know, I don't think there's enough African history in Brian Eno. So let me end with just a few words about applications that we've found for this. And you can go to our website. The applets are all free. They just run in the browser. Anybody in the world can use them. The National Science Foundation's Broadening Participation in Computing program recently awarded us a grant to make a programmable version of these design tools. So hopefully in 3 years, anybody will be able to go on the web and create their own simulations of their own artifacts. But we focused in the U.S. on African-American students as well as Native American and Latino. We found statistically significant improvement with children using this software in their mathematics class in comparison with a control group that did not have the software. So it's really very successful teaching children that they have a heritage that's about mathematics, that it's not just about singing and dancing. We've started a pilot program in Ghana. We got a small seed grant just to see if folks would be willing to work with us on this. We're very excited about the future possibilities for that. We've also been working in design. I didn't put his name up here. My colleague Kerry in Kenya has come up with this great idea for using fractal structure for postal address in villages that have fractal structures. Because if you try to impose a grid structure postal system on a fractal village, it doesn't quite fit. Bernard Tschumi at Columbia University has been interested in using this in a design for a Museum of African Art. David Hughes at Ohio State University has written a primer on Afrocentric architecture in which he's used some of these fractal structures. And finally, I just wanted to point out that this idea of self-organization, as we heard earlier, you know, it's in the brain. It's in it's in Google's search engine. Actually, the reason Google was such a success is because they were the first ones to take advantage of the self-organizing properties of the web. It's in ecological sustainability. It's in the developmental power of entrepreneurship, the ethical power of democracy. It's also in some bad things. Self-organization is why the AIDS virus is spreading so fast. And if you don't think that capitalism, which is self-organizing, can have destructive effects, you haven't opened your eyes enough. So we need to think about, as was spoken earlier, the traditional African methods for doing self-organization. These are robust algorithms. These are ways of doing self-organization, of doing entrepreneurship that are gentle, that are egalitarian. So if we want to find a better way of doing that kind of work, we need look only no farther than Africa to find these robust self-organizing algorithms. Thank you.